And we are now recording. We'll go from current slide. And let me go over these announcements. I think I may have done these before, but tell me if I have. I'll tell you about the College Transfer Day coming up in February. Okay, both campuses. On the 12th, it'll be on the Birmingham West Campus, 9:30 to 11:30. Building B, Academic Hall. I think they set up tables all up and down the hall there. And on Thursday, February 13th, it will be 9:30 to 11:30 here on this campus in this building. And they say the campus cafeteria, but what I think they mean is the faculty staff dining room. I don't know that for sure, but that's what my guess is. I hear some of the schools that have been invited. It's a lot of them, so be prepared that day to visit us. Now, this is something I had some interest in my last class. I hope y'all will be interested too. This is the summer research program for the Center for Power Optimization of Electrothermal Systems. The acronym for that is POETS. Okay, and they're looking to recruit minority engineering students to work at 3 of the 4 institutions this summer: University of Illinois, Arkansas, and Howard University. 10-week internship places undergraduates to academic research fields of mechanical, electrical, and materials engineering. The students are paid a $5,000 stipend to go for 10 weeks. They pay you $500 a week to go. Now, how they pay, whether it's once a week or one, I don't know how they do it, but they pay you $5,000 total for the 10 weeks. You receive free housing, which I think includes free food, and they pay you, get you there and back airfare 2 ways, one time, 2 ways. Okay. And then the learning opportunities are priceless. Okay, so there's lots of things. There's much more in the flyer here, a little bit more in the flyer here. So feel free to look at either one. The deadline, I forgot to mention this in my first class, is February 15th. February 15th is the deadline. All those things are coming up February. All right, now I'm pretty sure we did example 5. Okay, that was finding an arc length. I remember doing that. Any questions on that? Okay, and we did linear speeds and angular speeds, right? And then did we do sectors of a circle? I think that's where we left off, and we're going to start this time. Did we do this? No, okay. All right. So this is the top of page 266. Any questions on anything we've covered so far? All right. Now, here's a definition. A sector of a circle is the region, that means area, bounded by 2 radii. There's a radius, there's a radius. Radius is from the center of the circle to a boundary, just as long as it's not the same point on the boundary. Bounded by 2 radii of the circle and the intercepted arc. There's your theta. Okay? That's the definition of the sector of a circle. It's an area, a region. Okay? It's the pink part in there. Okay? Now, this is the formula for the area of a sector of a circle. For a circle of radius r, like that first one was, the area A of the sector of the circle within that central angle theta is 1/2 pi r squared theta. Now, the reason I always said it backwards is the way I like to remember it's 1/2 theta r squared. Now the reason I do that, I think of pi r squared, okay? Because that's how I think of area of a circle. So it's 1/2, not pi, but theta r squared. Theta, pi, of course, measures an angle. Theta measures an angle. Guess what theta is measured in? Radians. This formula will not work if theta is in degrees. theta must be in radians. Okay? Now let's go back to that figure. And I use this just as sort of a help. This sector looks a little bit like a triangle, doesn't it? Not quite, but a little bit. And what's the area of a triangle? Let me get my pen set up. Anyone remember the area of a triangle? This is called the height. This is called the base. Second?
270.
270. Height. No. Okay. Area. Based on base and height. Area of a triangle is 1/2 the base times the height. Remember that? If you put this triangle this way, then you have a parallelogram, right? Just flip this over. And then you cut off this part and paste it in here, and now you have a rectangle. The base this way, the height that way. Well, this is exactly half of that. You threw that off and had it. So it's 1/2 the base times the height. Okay. This may not be helpful then. Okay. That's the area of a triangle. Now let's just imagine this as sort of a triangle. Here would be your base, the radius, okay? The height here, this isn't exactly, but let's just imagine that arc length was your height, okay? The arc length is r theta, right? And if you use the same type principle, the area would be 1/2 the base, which is r, times r theta, which is 1/2 r squared theta, or theta r squared. And that's exactly what we've got here. Okay. Now, that's not exact. It doesn't work for every case, but that's the way I remember it. It makes it easier for me. But if you don't like that, use your whatever mnemonic device you want. Okay, but this is how you get the area of a sector of a circle. Okay? Now, whoa! Next comes example 8, and they want us to figure this. Now let's see if I can get a little more room on a slide. I think that gives me a little more room, doesn't it? Okay. Says here, a sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. So I'm going to try to do this. Here they show the fairway, something like this. Here's the sprinkler head down here, okay, and it does 70 feet. I think I'll write that elsewhere. "70 feet." You hear it? Okay. And it goes to here 70 feet. Okay. And it goes anywhere in there 70 feet. Now, I don't have it drawn right. This is supposed to be 120 degrees. The one in your book's a little bit better if you have a book. If you don't have a book, you have to settle for mine. Okay? Then, what is the... Find the area of the fairway watered by that sprinkler. So in other words, what we're interested in is this area here. Okay. So, thank you, all right? Okay. All right, good deal, thanks. How do we get the area here? What's the formula? Area of a sector is 1/2, second, r squared, theta. Okay, so how do we compute that? I can do the 1/2. What's your r? 70 feet. And we're going to square that. And what's your theta? Ha! Very good. You've got to convert that degrees to radians. So how do we do this? We have 120 degrees. We're going, that's not squared, that's a degree. We're going to multiply this by blank blank to get so many radians. Now radians, remember, isn't really a unit, but we're going to use RAD as if it was. The first blank is for numbers. Forget about those for now. Always put the units in the place. The second blank is for units. What unit goes where? Degrees in the bottom, radians on top, right? Now, how many radians make up a degree? How many degrees, or how many degrees make up how many radians? What about it? 180 what? 180 what? 180 degrees is pi radians. Remember? Pi radians, okay, is 180 degrees. All right, now I can do something. I'm going to cancel out my degrees here. I'm going to wipe out my zeros there. That's dividing by 10. Any common factors between 12 and 18? 6. So 6 will go into 12. Twice. 6 will go into 18. 3 times. So this is 2 pi thirds radians. That's what goes here. 2 pi thirds. There's your degrees, your angle in radians. All right. Going to get some fairly big numbers here, but that's okay. We can live with them. 70 squared is 4900 times 2 pi thirds. Hey, why didn't I see this before? The 2's can cancel out, right? Now, I don't think 3 will go into 4900 at all, because 4 and 9 is 13. Yeah, that's not divisible by 3. So, there's your answer. 4900 pi thirds. Or, you can approximate it because the boss doesn't understand pi's at all, so if you approximate that, what do you get? 4,900 times pi divided by 3. It's going to be something just a little bit more than 4,900. I'm going to guess 5,000 or so. You tell me. $4,900 times pi divided by 3. Any answer? It's going to be pretty big.
5,131.
Yep, that's good. You can stop right there. You can put 3 decimals, but you really don't need them. Technically, you only have, at best, 2 significant digits here. So basically, 5,100 would be close enough. But it does have units with it, and this is right here, square feet. So that would be the area watered by the thing. The book uses all 4. In reality, 5,100 square feet would be as precise as you could actually say. Now, I don't know. Did you catch how I estimated? Pi is just a little bit more than 3. So this ratio here, pi thirds, is a little bit more than 1. So this is just something a little bit more than 1 multiplied by 4,900. I said something greater than 5,000. Not a bad guess. Not exact, but not a bad guess. All right, any questions? Now remember, after every example in your book, there is a checkpoint, okay? And there's one here. Please do those as soon as you can after class. All right. Now, the next thing in the text is the exercises 4.1. And the first part of those exercises is vocabulary, okay? So let's fill in the blanks. 2 angles that have the same initial side and the same terminal sides are blank. Coterminal, exactly. Have the same side, coterminal. Okay, very good. Number 2, 1 blank is the measure of the central angle that intercepts an arc length equal to the length of the radius of the circle. 1 blank is the measure of a central angle that intercepts radian. Exactly, radian. That's equal to the radius of the circle. That's the definition of a radian. Two positive angles that have a sum of pi halves are blank angles, complementary angles, they complete, and two positive angles that have a sum of pi are supplementary angles. Perfect. Number 4, the angle measure that is equivalent to the rotation of 1/360th of a complete revolution about an angle's vertex is 1 degree. 1 degree. Okay? Pi is way more than 1 degree. Okay. Number 5. The blank speed of a particle is the ratio of the arc length traveled to the elapsed time, and the other blank speed of a particle is the ratio of the change of the central angle with respect to the elapsed time. Length per time is what length? What speed? Length, linear, right? And the speed of ratio of the change of the central angle with respect to time is the length to time is linear, angle to time is angular. Length to time is linear, length is a line, and the angle to time is angular speed. Okay. Number 6. The area A of a sector of a circle with radius r, central angle theta, where theta is measured in radians, is given by the formula just did. That's what?
A 1/2 r squared theta.
R squared theta, exactly. 1/2 r squared theta. A is equal to 1/2. Okay, that's your vocabulary for 4.1. Your homework exercises are any of the either 7 or 9. They're both a Calc Chat. 11's a Calc Chat. It has 2 parts. 13's a Calc Chat. It has 2 parts. 15's at both Calc Chat and Calc View. It has 2 parts. 17 or 19, they both have 2 parts. They're both a Calc Chat. 17's a Calc View. Either 21 or 23, they're both a Calc Chat. 25's a Calc Chat. 27's a Calc Chat. By the way, both of those have 2 parts. 29's a Calc Chat and Calc View. It has 2 parts. 31 or 33, both a Calc Chat. Both have 2 parts. But 33 is a Calc View. 35 has 2 parts. It's a Calc Chat and Calc View. 37 has 2 parts. It's a Calc Chat and Calc View. Either 39 or 41, both a Calc Chat. 43 or 45, both a Calc Chat. 47 has 2 parts. It's a Calc Chat. Now that's that one that uses degrees, minutes, and sometimes even seconds. So we didn't do an example like that in class. If you have any question about that, please ask. And going the other way, doing from decimal degrees, 49 has 2 parts. It's a Calc Chat, but it's going back to degrees, minutes, and seconds. So it's going just the 2 different ways of mentioning that. Okay, finding arc length. 51 is both Calc Chat and Calc View. 53 is a Calc Chat. 55 is a Calc Chat. 57 is a Calc Chat and Calc View. Now 59, really don't care for these too much because they're giving you something that's wrong and saying you find why it's wrong. I hate for them to give you something that's wrong. You'll say, oh, I saw that in the book. Well, but it was wrong, okay? But they have big X's in it, red X's, to indicate they're wrong. But, you know, not a bad exercise to find out what's going wrong with it, okay? Earth, Space, Science, 61 should be at Calc Chat. And then other applied problems, 63 is a Calc Chat, 65 or 67, they're both a Calc Chat. 69 is an area problem, it's a Calc Chat. 71 and 73 are both true false, there it should be a Calc Chat. There's a writing exercise at 75 if there's something in there that leads you to a potential paper topic. I don't see it myself, but maybe you do. And then you can think about doing 77. It should be at CalcChat, and 79 is a proof. Especially you math majors, if there are any of you, you probably want to do a few proofs just for funsies, because you'll probably see them in later classes. Now, there was something I was going to say about one of those. I can't remember what it was now. Oh, I was going to say this. This, one of my smaller classes, actually I've received 2, not just 1, but 2 research papers already. Way to go, folks. Okay. Any questions then on 4.1? Oh, in the book, those go from 267 to 269. Any of the odds on any of those pages. Okay. Any other questions before we move on? All right, let's get through this and go to 4.2. For those who may have come in late, didn't realize I'm having trouble seeing because I forgot and left my glasses at home. So if I'm doing a lot of blinking, that's why. I had, about a decade ago, had my left eye had a cataract removed and they put in a distance vision, but my right eye was still fine for reading and stuff. But then this past summer, I had the cataract removed from that because I was having trouble reading, and he put it on a distance that's in between reading and the computer screen. So I can't do either one easily but it's affixed. I can't adjust anymore because they're fixed lenses now. So reading glasses help, but I've forgotten and left them at home. So sorry about that. So here's my slideshow. Okay. There it is. Still in Chapter 4, Trigonometry. We'll be here quite a while, folks. 4.2 is trigonometric functions, and we'll start with the unit circle. Now, I think I mentioned to you before, when I did my first stint in trigonometry way back decades ago, we always started with triangles, the measure of triangles. That's what trigonometry stands for. But most of the modern texts that I've seen start with the unit circle. What we did the triangles first and then saw how it applied to the unit circle. To me, that made perfect sense. Most of the books these days start with the unit circles and then expand it to be triangles. Works either way. I just like the other way better, but there must be a reason they do it. So what we're going to do is identify a unit circle. And that almost by its name tells you what it is. It's a circle whose radius is 1. Who knows? 1. Okay? And describe its relationship to real numbers. Okay. Unit circle, what's its relationship to real numbers? Well, they mean certain real numbers, and we'll talk about this. We'll evaluate trigonometric functions using the unit circle, and we'll use domain and period to evaluate sine and cosine functions. That's our first 2 trig functions, and use a calculator to evaluate any trigonometric functions. Okay? So obviously we're going to do a little bit more than just sines and cosines. So let's start with the unit circle. I already gave it away. The 2 historical perspectives of trigonometry incorporate different methods for introducing trigonometric functions. One perspective follows here is based on the unit circle. The second one is based on triangles, right triangles. I like the right triangles better, but we're going to start with the unit circle. Okay. Consider the unit circle. This is a circle of radius 1. And they drew the circle with the center at the origin, so 1 unit in any direction gets you on the circle, whether you're on the axes or not, or anywhere else. That's still a radius of 1. Everywhere the radius is 1. Well, for any point on the circle, even these, for any other point, x, y, then if the radius is 1, your think I have to change my pen here. Let me do that. Let me do that. There we go. Pick a point here. X, Y. Here's the X coordinate. There's the Y coordinate. Okay? You draw out here X, and here's Y. There's X, there's Y. Here is the hypotenuse of that right triangle, right? So here we are, right down to triangles again, right? And what is true about two sides of a triangle and the hypotenuse? And we know that hypotenuse is equal to 1. Does the name Pythagoras ring a bell? Pythagorean theorem, and how does that go? A squared plus B squared equal C squared, where C is always the hypotenuse. A is one side leg, B is the other side. So for us, that would be X squared plus Y squared is equal to 1 squared, which is 1. So every point on a unit circle has to meet that criteria. Any point X, Y, whether it's here, 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 wherever they are, every point X, Y on there has to be X squared plus Y squared equal 1. Pythagorean theorem. They didn't show the X, Y coordinates, but I put those in. Okay? Now, certainly this works because 1 squared plus 0 is 1. 0 squared plus 1 squared is 1. Negative 1 squared, 1 plus 0 is 1. And 0 squared plus negative 1 squared, which is 1, is 1. So if those four work, any point X squared plus Y squared is 1. That defines a unit circle with the origin at the center. Okay. Got it? Okay. Now, here's where they have you using your imagination. Imagine wrapping the real number line. So we're going to get the real number line, but we're going, rather than have it go in the horizontal direction, we're going to have it go vertical. Okay? We're going to start at this point right here where theta is equal to 0, right? So horizontal, positive horizontal axis. Okay? So we'll put our real number line going up here, and any value on this line we're going to name t. You might say yt. It's just a parameter. That's all. Okay? So we're going to imagine wrapping this. See, a real number line is usually a line. But we're going to bend it and wrap it along this unit circle. Then, whatever the measure of t is along that arc of the circle, it's going to end at some point xy. Okay? And we know that x squared plus y squared is equal to 1 because this is a unit circle. And for any t greater than 0, then this will be that. Now, this unit, this length here, wrapped around the circle is t. You might say, why are we doing this? And that's a good question. Hang with it and we'll see. Imagine wrapping the real number line around the circle with positive numbers corresponding to counterclockwise wrapping, negative numbers corresponding to clockwise wrapping. Okay, sounds like Christmas, doesn't it? Okay. Now, here's the negative. Negative being downward, this would be a negative number, t. Okay? So that angle theta. Okay. There's what we're going to be talking about. When it talks about real numbers, that's the real number t. Okay. And again, to me, this isn't the easiest way to present this. This is how they always do it for the unit circles. But we can live with it. As the real number line wraps around the unit circle, each real number t corresponds to a point xy on that circle, just like it showed. And you wrap that around, if that t was 4, that wouldn't have been the number, but whatever it was wrapped around there, that corresponds to some point xy. For example, the real number 0, okay, that corresponds to the point 1, 0, because you haven't moved it either direction, up or down, so that would just be 1, 0. Moreover, because the unit circle has a circumference of what? 2 pi, because one time around, if radius is 1, the circumference is 2 pi r, so that would be 2 pi. The real number 2 pi corresponds to the point 1, 0 again. So 0 corresponds to 1, 0, and 2 pi corresponds to 1, 0. Guess where pi would correspond to? Negative 1, 0. Where would pi halves correspond?
0, 0.
0, 1, okay? 3 halves pi. 1 pi plus another half pi, 3 halves pi.
0, negative 1.
0, negative 1, okay? You got the idea. Those are real numbers corresponding to those points that are on your axis, okay? But guess what? Every other point on there corresponds to some xy. Those were the easy ones, okay? In general, each real number t also corresponds to its central angle. Central angle for that first one was 0. Central angle for the next one was 2 pi, okay? This central angle, anywhere in there, that's going to be your theta in standard position, which is from your initial side being the positive x-axis, and then terminal side wherever it lines up, going counterclockwise. Whose radian measure is t. Okay? Because if t is that arc length, radius is 1, the arc length is equal to t. Okay? The angle is equal to that arc length. Okay? With that interpretation of t, the arc length formula, S is equal to r theta. But if your r is always 1, S is equal to theta. So S is your, why they use so many different lengths? S stands for arc length, R stands for radius, that's 1. Theta stands for your the angle in radians. So T, if that length is T, that's what they're defining. Bend that around there, that's going to be your arc length. T is equal to theta. Okay, R is equal to 1. Indicates the real number T is the directional length of the arc intercepted by the angle theta, given in radians. Okay? The angle given in radians, but T is the length. Okay? So it seems rather strange that you would have S length, feet, yards, miles, is equal to so many radians. Doesn't sound like that's right. Well, the reason is your R is equal to 1 inches length. Yeah, mile. That's where the unit comes from. But with 1 there, we don't even see the number, so we don't realize it's being set. But remember, a radian is not a unit. It's just a ratio. Okay. Now, whoa. Yep, that's all there was there. We move now to the second subtopic here, the trigonometric functions. From the preceding discussion, it follows that the coordinates of x and y are two functions of that real number t. Okay? The real number t is that arc length that wraps around the circle, the unit circle, and x and y depend on how long that t is. You can use those coordinates to define 6 trigonometric functions of t. And here they are. I don't like the order, but there is a reason for it. Sine, cosine, tangent, cotangent, secant, and cosecant. That's the order I like. There is a reason they give them in this other order. Those are normally abbreviated as SIN. Don't count that as sin, that's sine. Cosine is COS. Secant is SEC. Tangent is TAN. Cotangent is COT. So would cosecant be COS? No, because that's what cosine is. So we can't use COS, so we drop the vowels and it's CSC. So cosecant would be CSC. The other 5 are all the first 3 letters. The cosecant is the first 3 consonants, CSC. So that's what we usually call them. Now, what are they? They are functions of the variables here. Okay. Technically, they're functions of t, functions of t related to these variables. That's how I meant to say it. And here's those relationships. If t is the real number, x, y is that point on the unit circle. Now this is because it's a unit circle. This is sort of what I don't like about doing unit circle first. You get used to seeing these identities, these definitions, and you think they're always true. These are only good for the unit circle. So get that. The sine of t is always equal to y on the unit circle. Not anywhere else, but on the unit circle. The cosine t is the same as x. The tangent t is the ratio of that y to x. As long as, of course, x is not 0. And where is x 0? What two angles which also correspond to the t's? Where is x equals 0? Second? 90 degrees, or we're in radian time. Pi halves and 3 halves pi's or negative pi halves. Exactly. Okay? Now, so tangent can't be defined at pi halves or at 3 halves pi or negative pi halves. Okay? Now, I like to go this way around. The cotangent is then the reciprocal of the tangent. So x over y. But now y can't be 0. Where is y equal to 0? 0 and yeah, or pi. You like okay. Okay, 0 or pi, or any multiple. Then secant is 1 over cosine. Okay? But of course that can't be defined when x is 0, which is the same as it was for tangent. Pi halves, 3 halves pi, or negative pi halves. And cosecant is 1 over sine, so that's 1 over y. Now y can't be 0, that's the same as tangent. Now, what this leads to, sine and cosine are defined for all real numbers. No limitations whatsoever. Tangent and secant, x can't be 0 or any multiple of pi. Well, no, I'll say that right. X can't be 0, okay? And that happens when t is pi halves or negative pi halves, 3 halves pi, or any odd pi, odd halves pi, okay, any half pi, okay, sine, tangent, and secant are not defined. Cotangent and cosecant are not defined for any multiple of pi, okay, 0 pi, minus pi, any multiple of pi, any half pi, tangent, and secants are not defined. Hang on to those. Okay? Did y'all get that? Did y'all need it on? Okay. In the definitions of the trig functions, note that the tangent and secant are not defined when x equals 0. That would be at your half pi's and any half pi. Okay? Corresponding to 0, 1 or 0, negative 1 or any time when x is 0. It follows that tangent or pi halves, secant, sine is undefined. You can't ever, they don't have any value there at all. Similarly, the cotangent and cosecant function is not defined when y is equal to 0, and that would be any place where the theta is, or your t is 0 or any whole pi. Not half pi, but whole pi's. 1 pi, 2 pi, 3 pi, negative 3 pi, whatever. So those places, cotangent are undefined. Anytime your y is 0. Now, in this figure here, we're breaking down a unit circle into 8 equal parts. Okay? This will be all the way around the circle is how many? 2 pi. Halfway around would be pi. half of that would be pi halves, and half of that would be pi quarters. Okay? So these are your equal, divided into 8 equal parts: 0, pi-fourths, pi-halves, 3/4 pi, pi, 5/4 pi, 3/2 pi, 7/4 pi, and 2 pi. All the way around. Now, they throw up some values here for your x and y without telling you why. Okay? I'm going to tell you why. What's true about any x, y value anywhere on the unit circle? Say again? The radius is 1. So what does that have to do with, say, an xy here? X, y. Had it a few slides ago. What would always be true about any point x, y on a unit circle? You got it. X squared plus y squared is equal to 1. Anywhere on the unit circle, that's got to be true. Now, let's take this line right here. It's exactly halfway between 0 and pi halves, pi quarters. That is the, remember we used to call that the identity function. Your y value is equal to your x value, because this exactly splits that quadrant in two, right? Exactly. So your y value is exactly equal to x value. Wherever you are there, the y value is equal to x, right? So now we know that x is equal to y, or y is equal to x. Okay, let's take that and plug it in either one of the other two. Which you want to plug in, y for x or x for y? I really don't care. Y for x, okay? So instead of x squared, we'll put y squared plus y squared is equal to 1, right? Because x equals y, right? Combine like terms, what do we have? Combine like terms. Y squared plus y squared is how many y squareds? 2y squared, right? Is equal to 1, right? Agreed? Okay, let's divide both sides by 2. Let's solve for y. So you have y squared is equal to 1/2. Now what can you do? I want to solve for y. I don't care what y squared is. I want to know what y is. Take the square root of both sides. Okay? It could be a plus or minus, so we could do that. So y is equal to plus or minus the square root of 1/2, which is, square root of 1 is 1, so it'd be plus or minus 1 over the square root of 2. Can y'all read that okay? Okay. Now, quite often they don't like having radicals in the denominator. Now, this goes back to ancient history, not that ancient, before calculators, BC. No, okay. Way back, okay? Not that long ago, folks. And here's why they didn't like dividing by a radical. Does anyone know what square root of 2 is? 1.414 blah, 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 blah. It's an irrational number. It goes forever. It never repeats the thing. It can't be written as a ratio, as a rational number. So it's irrational. Well, if you're dividing 1 by that number, you have a lot of decimal places. You have to move the decimal. This would put the 0.0 here, move it there. That division is miserable. So they don't like having radicals in the denominator. How did they get over that? Ever hear of rationalizing a denominator? Let's multiply the denominator by square root of 2, but multiply the numerator by square root of 2, right? What's your new numerator now? 1 times root 2 is root 2, but root 2 times root 2 is 2, isn't it? Okay? Now, to get that, if this is 1.414 blah, 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 divide that by 2, you get 0.707. 0.07. I could divide that in my head. I can't divide this in my head. Okay, so that's why they rationalize the denominator. So, about half the time in this book, maybe more than that, they'll always write things in rationalized denominator. But every now and then you'll see them not do that. So get used to it. So, guess what? There's what your y value is, right there. Right? Or minus that. And that would be that. Remember we had the plus or minus here. That's going to be this one. And here it's plus again. Here it's minus again. But on your main diagonal there, your x is equal to y, right? So this would also be root 2 over 2. Down here, though, the x's are the same, the y's are the negative, so that's the same. Over here, the x's are negative, but the y's are the same. Down here, they're both negative, right? So that's where they came up with the root 2 over 2. You could have said it 1 over root 2. That's the same number. This is just written with rationalizing. So now we know for pi fourths, pi halves, we already knew that one. Okay, let's go back in. Okay. We know these are the xy values. We know that was 1, 0, root 2, root 2, root 2 over 2, root 2 over 2, 0, 1, negative root 2 over 2, root 2 over 2, negative 1, 0, negative root 2 over 2, negative root 2 over 2. That's on that line that they're the same. 0, negative 1, and root 2 over 2, negative root 2 over 2. But remember, we just have said what our, I'm going to erase a lot of this. Is that okay? All right? Okay. Now, what did we say the sine function was? Let's start with the number 0. Sine of 0 is, what was sine? The y value. And what's the y value when t is equal to 0? Zero. Okay, I thought you might catch on. What's the sine when t is equal to, this was pi fourths. What's the y value equal to? What is it? Root 2 over 2. Let's go to the next one. Sine of pi halves. What's the y value equal to? 1. The sine of 3/4 pi? What's that? Okay. Yeah, your t value is your radian measure. Sine of pi fourths is root 2 over 2. Sine of pi halves is 1. Sine of 3/4 pi is root 2 over 2. Sine of pi is 0. Sine of 5/4 pi is minus root 2. So you know your 6 trig functions. Well, you know your sine function for every one. What's the cosine? The x value. So the cosine of 0 is, if you can read that 1, cosine of pi fourths is root 2 over 2, cosine of pi halves is 0, cosine of 3/4 pi minus, sine of this is minus 1. You know all 6 of those, right? All 8 of those, okay? How about tangent?
X over y.
Y over x.
Yeah, y.
Okay, sine over cosine. 0 over 1 is 0. Root 2 over 2 over root 2 over 2 is 1. Tangent of pi fourths is 1. Tangent of this is 1 over 0. Undefined! You can't do it! You can't do it when x equals 0, right? Because it's y over x. This one is? Again? Root 2 over 2 over negative root 2 over 2. What does that come out to be? Negative 1. Okay, down here. Again? Y over x. 0. That's okay. This one? Positive 1. This one? Undefined. This one? Negative 1 again. So you know your tangent function. How about the cotangent function? What's it? Let me erase some stuff. Okay, x over y, right? Cotangent is x over y, right? So what would this be? Undefined. This one would be 1. This would be 0. You can do 0 divided by 1. You can't do 1 divided by 0. This one? Negative 1. This one? Undefined. This one? Positive 1. This one? 0. This one? Negative 1. You know all 8 of those cotangent functions. Okay? How about secant function? What was secant? 1 over x. So this would be? No. 1. 1 over 1 is 1. Right? This one would be? Now here's, okay. Here's where you go back to what I like to call the other form, 1 over root 2. Remember, that's what that originally was, right? We rationalize the denominator. Since you're going to invert it, we're okay to have that radical in the denominator because when you invert it, it just becomes root 2 over 1. So that's root 2, right? 1 over x. This will be root 2. This will be undefined, 1 over 0. This would be negative root 2. Reciprocal of that. This would be negative 1. This would be negative root 2 again. This would be undefined. This would be, say again, positive square root of 2. Perfect. How about cosecant function? 1 over y. So this one would be undefined. This one would be root 2. This would be 1 over y. Okay. This one would be root 2. This would be undefined. This would be negative root 2. This would be negative 1. This would be negative root 2. Okay. Now, something I don't know if you realize there or not. Okay? Your sine and your cosine function always stay between 0, 1, negative 1, 0. They always stay between -1 and 1. Always. Sine and cosine always between -1 and 1. Your tangent and cotangent can be anywhere. Negative infinity to positive infinity. But your secant and cosecant, they can be 1 over 1, but not 1 over 0. That's undefined. So that's going to positive infinity. Okay? This is a root 2. That either one. This is either positive infinity or 1. But these are always, root 2 is greater than 1. So your secant and cosecant are always greater than 1 or less than -1. They're never in between -1 and 1. Cosine and sine are always in between -1 and 1. Secant and cosecant, being the reciprocals, are always outside that. Greater than +1, less than -1. This tangent and cotangent, they can be anywhere. Minus infinity, positive infinity. All right. Now, let's take that circle and divide it, that unit circle, divide it into 12 equal arcs. Why would we want to do that? Well, that gives us our favorite angles. Okay? Because when you divide in 12 equal arcs, Well, two equal arcs would be, this would be, all the way around this, 2 pi, halfway around this, pi, quarter way around this, pi halves. Now this time we're going to do the pi halves divided by 3. So this will be pi, this will be pi thirds, this will be pi 6, because it's pi halves divided by 3 will be pi 6, then pi thirds, then pi halves, then 2/3 pi, 5/6 pi, pi, 7/6 pi, 4/3 pi, 3/2 pi, 5/3 pi, 11/6 pi, and finally back to 2 pi again. Okay. So that's dividing by 12 equal pieces. Now, if you remember back, these were some angles we liked. We could say things about them. Okay. Say things about any of them, I guess, but these are pretty nice ones. Let's see if we can figure out what the XY values. They have them identified for you. That's cheating. You should have been able to figure these out on your own, right? So here's what we're going to do. We're going to take I like, so akin to you, I think, I like to use degrees, because I'm thinking degrees better. Okay. Now, obviously, this is a radius, right? So that's unit circle, that's going to be 1. Every one of these is going to be a 1, right? Okay. We can take any 2 that we want to. But let's take these 2. So this is 1 this way, and this is 1 that way, this is 1 this way. Okay. Now, these 2 add up to what? If you add 2 of those together, this is pi 6, right? And another pi 6 gives you pi thirds, right? Okay. Now, these 2 sides are the same, both 1. Now the question is, if this angle here is pi thirds, okay. Now I'm going to do something that's a little strange, but I'm going to do it. I'm going to connect these 2 dots, okay. Now that forms a triangle, doesn't it? This is side 1, that's side 1. We don't know what side that is. But what about the angles? What do the 3 angles have to add to? Anyone know? 3 angles of a triangle always add to 180 degrees. And in radians, that's how much? Pi. So we have, okay, so that's one observation. Another observation, even in my ugly drawing, doesn't this angle look to be the same as that angle? Right? Yeah or nay? Okay. They sure do. Well, here's why. Because the opposite sides are exactly equal to each other, so the angles have to be equal. Okay? A little bit of geometry there. Okay? So if we have that, let's name this. Pick a name for those 2 angles. And we know they got to be the same, right? So pick a name for them. Alpha. Okay. Call alpha. Okay, so these 2 are alpha. So you just told me that pi thirds plus alpha is 2 alpha. It's got to equal, what do you say? Or pi. Okay. Now, because this is in thirds, I want to write that as 3/3 pi, right? Isn't that pi? Okay. You in agreement? Okay. So how do we solve for alpha? Find alpha. Pretty easy, isn't it? What would you do? Subtract pi thirds from both sides. Okay, that goes to 0, and this gives us 2 alpha is equal to, if you subtract 1/3 pi from 3/3 pi, what do you have left? 2/3 pi. Yay or nay? Okay, and then what do we do if we're trying to solve for alpha? Divide by 2. Guess what alpha is? Pi third. Hey, that's the same as this one, isn't it? So this is what kind of triangle? If they all have the same angles.
This is the right triangle?
No, it isn't. None of those angles are 90 degrees. They're all pi thirds. If they have equal angles, guess what the sides are?
Equal.
Equal. And if this is 1 and that's 1, guess what this one is? 1. And if this is exactly bisected by this, up here would be, if that whole side is 1, this would be 1/2. The angle is pi 6, but the length there is 1/2, right? Hey, we just got the y value, don't we? 1/2. Okay? So you just confirmed this. That's going to be 1/2. Now, what else can you tell me? This is what kind of circle? Unit circle. And what's true about every unit circle? X squared plus y squared is equal to 1. And you just told me the y is 1/2. So x squared plus 1/2 squared is equal to 1. Agreed? Okay. So let's do that. X squared plus, what's 1/2 squared? No, it isn't. I didn't say double. I said squared. Say again? 1/4. And how many fourths is 1? It's what? How many fourths is 1? 4/4, right? I don't like subtracting fractions, so I'll try to make them as easy as possible. Okay? So 4/4. So now let's solve for x. X squared is equal to, what do we do here? I'm sorry. I'm jumping ahead. Okay? How do we solve for x? Subtract 1/4 from both sides. What does that give us? X squared is equal to 3/4. I don't care what x squared is. I don't know what x is. What do we do? Take a square root. So x is equal plus or minus the square root of 3/4, right? But that's the same as plus or minus the square root of 3 over the square root of 4. Well, what's the square root of 4? So now we know what the x is. Square root of 3/2 or minus the square root of 3/2 right here. Wait a minute. I went to the wrong one. Okay. Square root of 3/2 or over here minus square root of 3/2. Okay. Now, if we had done these two and did them that way, we'd have the same thing if we did these two. This would be exactly halfway between, draw this line here. But everything works out the same. If this is 1, this will be then 1/2. So this is going to be 1/2 root 3/2. The x value here is 1/2. The y value is root 3/2. Here the y value, x value is root 3/2. The y value is 1/2. Okay, so these plot around the circle like that. And then this is the opposite x, same y. Opposite x, same y. Opposite x, same y. Opposite x, same y. Yeah, go all the way around the circle. And you've got those values there. Guess what you can do then? You can tell me all 6 trig functions at every one of those points. If you know the x, y values, you know the sines. You know the cosines. You know the tangent. You know the cotangent. You know the secants, and you know the cosecant, right? Because you know those relationships, right? Sine is always y, cosine is always, tangent is always y over x, cotangent is always x over y, and secant is always 1 over x, and cosecant is always 1 over y. So once you have the x, y points, you can fill in what the sine, the cosine, the tangent of each one of those things. You know them all. Right there, based on those points. Are we already out of time? No, okay, good. Huh? 5 more minutes, okay. I knew Chicory had left, and then it looked like people were beginning to pack. Okay. So there are your trig functions, and you know them for every one of those angles. If you can get the xy value, which we can for those are our favorites, dividing by 8, dividing by 12, we can get the xy value for every one of those. Okay? So that's what we're going to do. Oh, okay. To verify the points on the unit circle, this is doing what we just did. They just showed them to you, now they're going to verify. Note that root 2 over 2, root 2 over 2 also lies on the line y is equal to x, because y is equal to x, right? So by substituting y for x into the equation, you have, and this is exactly how we did it, x equals plus or minus root 2 over 2. Here's plus root 2 over 2, here's minus root 2 over 2. X value here, x value there. Okay? And then because x equals y, the y value can be plus root 2 over 2 and minus root 2 over 2. Plus root 2 over 2 and minus root 2 over 2. So you got all those points there. And because the point is on the first quadrant here, that root 2 over 2, the second quadrant will be minus for, oh, I haven't done that yet, but we'll get to that in a minute. We'll just stay in the first quadrant for now. Okay? So we got that. Now, we'll do the similar reasoning for the verify the rest of them and the other. When you had the other, this is root 3 over 2, 1/2. That even looks like it's exactly 1/2. And this is exactly 1/2 for x, and root 3 over 2 here. This is minus root 3 of, minus 1/2. This value, positive root 3 over 2, minus root 3 over 2, positive, minus root 3 over 2, positive 1/2. I'm doing my lines wrong. And all the way around. You can get that. You can evaluate trig functions for all of those, what they call the common t values. Those would be t equals 0, pi 6, pi quarters, pi thirds, pi halves, 2/3 pi, 3/4 pi, 5/6 pi. Every one of those you can do. Okay, those are what they call the common t values. Okay, and example 1 demonstrates that. So let's us do example 1. Evaluate all 6 trigonometric functions for each real number. Okay, and basically what I like to do, figure out the xy values. So if t is equal to pi 6, what's our xy value there? Let's just, first quadrant, just go up a little. What's the x value? Okay, maybe it would be helpful to draw a circle. What I like to do is draw the coordinates first and then draw. Actually, I'll draw the circle first and then coordinates. Okay, pi 6 would be this one right here. We know this is going to be 1/2. The y is 1/2. The x is root 3 over 2. All right. Let's do a timeout for a moment here. Let's put all those angles we like. This is pi 6, pi 4ths, pi thirds. That's not quite in the right place, but pi thirds, and pi. Okay. Let's write down the y values for each of these. Y value here is 0. Y value here is 1/2. Y value here is root 2 over 2. Y value here is root 3 over 2. Y value here is 1. You buy that? Yeah.
That's supposed to be pi or a half pi.
Say that again.
That's supposed to be pi,
Yeah.
1/2 pi.
Yeah, this is, oh yeah. Pi half, you're right.
What's
Sorry.
the one on the right? Next to the one, next to the one.
Say again.
The one on the right. On the bottom, next to the square root.
Okay. This is pi 6, pi, I can't write. Pi 6, pi 4ths, this one's pi 4ths, pi thirds, and pi halves, sorry. Okay, got that? Sorry, I wrote them wrong. let's look at the y values only. 0, 1/2, root 2 over 2, root 3 over 2, and 1. Okay. Well, this is going to seem strange, but it works. This is square root of 0 over 2. This is the square root of 1 over 2. This is the square root of 2 over 2. This is the square root of 3 over 2. And this is the square root of 4 over 2. Because what's square root of 4? 2. And 2 over 2 is 1. So this is my easy way of remembering this. You remember pi 6, pi 4, pi thirds, pi halves. 0, of course, sorry. The y value is 0 over 2, 1 over 2, 3, and 4. That would be 0, 1/2, 2 over 2, 3 over 3, and 1. That's the y value. Guess what the x values are? 0, square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Just didn't count much. Sorry about that. Once you got those, then the others are just going to be minus for the x's, positive for the y's, minus, minus, plus, minus. Right? So, the same values. Okay? So, let's go back to, if t is equal to pi 6, what's your xy value? Do the y first. It's easy. One half, and the x is root 3 over 2. Those always go together, because when you square this, you get what? Square root 3 over 2. Somebody do it. Okay, square root of 9/4, which would be, what's the square root of 9? 3/4 plus square this one. 1 over 2 square, and what do you get? 1/4. 3/4 plus 1/4 is unit circle 1. Okay, so every one of these have to be, your xy always have to, when you square them, they got to be 1. Okay, so once you figure out what the xy value is, right, then you can do it. What's the sign of pi 6? What's the sign on the unit circle? Go back. What sign? Y. And what's your y? 1/2. What's cosine? That's the x, and that would be root 3 over 2. What's the tangent? Okay, y over x, which I like to just do this. Imagine drawing a line there. Now that's a 2. My pen drags sometimes, and that makes it ugly. Let me write that better. Okay, the 2's cancel out, and this is going to be 1 over root 3. Right? Because the 2's cancel out. Well, guess what? Rationalize that, and what do you get? Okay, that is multiplying numerator and denominator by the denominator. What would that be? 1 times root 3 is root 3, and root 3 times root 3 is? Second? Is what? You may have said it, I don't hear well. 3, perfect. Root 3 over 3. Okay? Now let's do cotangent of pi 6. Now, what I like to do is go back to this one, right? And flip it. What do you get? Reciprocal.
Square root of 3 over 1. What is square root of 3?
Yeah, isn't that just root 3? Right? Before you rationalize, just flip it that way. Okay, secant of pi 6 is the flipping of that one. See, these are reciprocals of each other. So that would be 2 over root 3. But if you don't like having radicals in the denominator, multiply numerator and denominator by root 3. It's supposed to be a 3. So this would be 2 root 3 over 3. Strange but true. Okay? And the next one would be cosecant. And that's the easy one. It's the reciprocal of sine, which is, say again, 2. 1/2, flip that, and it's 2 over 1. Okay? You've just done it. You've got all 6 trig functions for t equal pi 6. So first thing you do, get your xy coordinates. Okay? Next thing you do, just plug in. Okay? That's it. So what's your xy, how much time we got? What's that? 6 minutes after? Well, guess what? There's no extra charge. Okay. So we'll pick up next time with the b part here. T equal pi fourths. Okay? All right. Homework exercises here will include either 5 or 7. They're both account chat. Nine or 11. They're both account chat. And you can start doing some of the odds, 13 through 21, but we haven't done many of those, so you don't, forget that. Just do 9 and 11, okay? I mean, 5 or 7 and 9 or 11, they're all account chat. That page 275. Yeah, and we're almost through with 4.2. You should finish that next time and move on to 4.3. Is it making sense, or is it going too fast, too slow? What you feel? Huh? A little too fast? Okay. We may slow down a little bit next time. Try to remind me of that. Okay.
It makes sense.
It is? Yeah. Good deal. All right. We'll pick up there then next time. Sorry I ran over. Not too much, but a little bit.
Can I take a picture of that page?
Sure, absolutely. You want the previous one too, or? Okay. This is 4.2. And you're just doing the, okay. And then the previous one was all those. You may have already gotten that. I don't know if you did or not. Okay. And this one and that. Okay, yep, that's it. Okay. Good deal.